Hello everyone, welcome to Angel's Classroom. In today's class, we are going to see about transistor configuration. First, let us see, when it comes to transistor, it consists of three terminals. We all know about it, okay. One terminal is going to be the input, another terminal is going to be the output, and the third terminal that is going to be common for both your input and output. Depending upon these terminals, a transistor can be connected in three configuration. First one is common emitter, common base and common collector configuration. This common emitter can also be called as grounded emitter. Common base is called as grounded base configuration and common collector is called as grounded collector configuration. First thing we are going to see is common emitter configuration. In this configuration, the base is going to be your input terminal, collector is going to be the output terminal and your emitter that is going to be a common terminal. Since it is common emitter terminal, I am going to ground that particular terminal. To determine the input characteristics, the collector to emitter voltage is kept constant, say for example initially at 0 volt. Now the base current is increased from 0 in equal steps by increasing your VBE in the circuit, that is your base emitter voltage. See this diagram, a curve is drawn between the base emitter voltage that is in your x-axis and the corresponding base current that will be marked in your y-axis. Initially, I am going to measure for VCE is equal to 0. Same procedure is going to be repeated for higher values of VCE and the corresponding base emitter voltage and base current is noted down. First thing, I am going to calculate when VCE is equal to 0. So, when VCE is equal to 0, your emitter base junction is going to be forward biased and the junction behaves as a forward biased diode. Hence, the input characteristics for VCE is exactly similar to that forward biased diode which we have studied in your first unit. See this diagram. So, when I am going to increase the voltage, so here in this N type, the electrons are majority carriers that is going to recombine with your positive terminal. So, here the recombination takes place and because of this the effective width of the base will decrease, hence it leads to a decrease in base current. But I have to get the same value of IB as for that of VCE is equal to 0. For that purpose, I am going to increase VBE voltage. See this diagram. For VCE is equal to 0, at 0.4 voltage itself I am getting the value, but when I am increasing the voltage, I will get the value for VCE greater than 0. To determine the output characteristics, the input side should be kept constant and we have to keep on changing the output voltage and thereby it shows an increase in current. So, here the base current is to be kept constant and collector to emitter voltage is increased from 0 in equal steps and collector current is noted down. Now, a curve is drawn between the collector emitter voltage in x-axis and collector current in y-axis at a constant IB for fixed value. Initially, for IB is equal to 0, a graph is drawn between VCE versus IC. Now, I am going to repeat the same procedure for higher values of IB and the corresponding emitter current and voltage is noted down. In a transistor circuit, IB is the input current and IC is the output current. You know about it. Okay, the first case is going to be the base circuit is kept open, which means IB is equal to 0. Now, a small collector current flows from collector to emitter. That current is called as collector to emitter leakage current and it can be represented as ICEO is equal to 0. This is the first case. Okay. Next thing, in CE configuration, the emitter base is always forward biased and collector base is reverse biased. I am going to calculate the value for collector current IC. This IC is a sum of part of emitter current that reaches the collector and collector emitter leakage current. So therefore, the part of emitter current which reaches the collector, that should be equal to IC minus ICEO. Now I am calculating the current gain beta. So the beta is equal to IC divided by IB, which is equal to IC minus ICEO divided by IB. This collector current IC is equal to beta into IB plus ICE naught. This is my equation number 1. Next thing is the relationship between ICBO and ICEO. We know this equation will be equal to 1 plus beta into ICBO, and the relationship among IC, IB and IBO, beta will be equal to alpha divided by 1 minus alpha. So this alpha and beta are the current amplification factors for both your common emitter and common base. Now I am going to substitute this second equation and first equation. Therefore, IC is equal to beta into IB plus 1 plus beta into ICBO. Okay. For a larger volume of VCE, that is your collector emitter voltage, what will happen? An early effect occurs. What is this early effect? So early effect is that when I am going to increase the collector based voltages, there will be an increase in this base current. When alpha is equal to 0.98, say for example I am taking this. So when calculating this beta value, its value is 49. When I am increasing this alpha value slightly, that is 0.985, then beta will be equal to 0.985 divided by 1 minus 0.985, that will be equal to, so by slightly increasing about 0.5 percentage, it's caused an increase in beta value for about 34 percentage. Next one, all the output characteristics of three configurations consist of three main regions. One is saturation region, next one is cutoff region, and the third one is active region. For a saturation region, see this graph over here. The region to the left of 0A, this hatched region is your saturation region, and the line 0A is your saturation line. In this region, both the junctions are forward biased. This is very important over here. Okay, here the junctions are forward biased. Now increasing in the base current value does not cause a corresponding larger change in collector current. Next one is my cutoff region. Here the region below this IB, so here I have mentioned 0 microamps in the graph, right? So that one is my IB. So the region below this is hatched, and that is my cutoff region. So in this region, both the junctions are going to be reverse biased. When the operating point of the transistor enters the cutoff region, this transistor is going to be in off condition. Next one is my active region. So the central region, in between the saturation and cutoff region, we have the active region. So here the emitter base junction is forward biased and collector base junction is reverse biased. For example, if I am using the transistor as a linear amplifier, it should be operated only in this region. Next topic is your transistor parameters. For all the configuration, we have 4 parameters. First one is input impedance, output impedance, forward current gain and reverse voltage gain. So this input impedance HIE, they have mentioned HIE. This is because the transistor parameters is also called as hybrid parameters or H parameters. Now HIE, it is defined as the ratio of base emitter voltage to the base current with VCE as a constant. This one is going to be similar to that of input characteristics. In input characteristics, what we did, we kept the output voltage as a constant and we keep on changing the input voltage and we measure the current. Okay. Now HIE is equal to delta VBE divided by delta IB. At that time, VCE is going to be a constant. Now, this typical value will ranging from 500 to 2000 ohm. Next one is output admittance. So admittance is inverse of your impedance. So the unit of admittance is mho, and HOE is equal to delta of IC, your collector current, divided by delta VCE, your collector emitter voltage. Here IB is equal to constant. So here typical value ranges from 0.1 to 10 micromores. Next one is your forward current gain. So this is defined as the ratio of collector current to the base current when VCE is kept constant, and the typical value ranges from 20 to 200. Next one is your reverse voltage gain, HRE. It is defined as the ratio of change in base emitter voltage to the collector emitter voltage. Here IB is kept constant. So it should be typically in the order of 10 power minus 5 to 10 power minus 4. So that's all for today. See you in another video. Thanks for watching.